So let we continue with our discussion of confidence interval estimation for various characteristics of the population. And this is the one which we wanted to discuss last time, but here we stopped. We need to estimate confidence intervals. And this time we are estimating the variance. Variance or standard deviation is one and the same thing. Just the square, one is the square of the other. For the variance of a normal distribution. So that means your population is still normal and you don't know what does this mean, and you do not know what is its variance, what is its standard deviation. Last time we saw that if we don't know these things about the population, how can we estimate a confidence interval for the mean of such a population? So this time we are interested in the variance of such a normally distributed population. How do we estimate this given a sample? Yes. Go ahead with your question.
सर इसमें हम assume कर रहे हैं कि normal distribution है या फिर given है?
Given है. Yeah. So, I mean, in practical problems, when you have no idea if the population is normal or not, you can, for most of the times, you can start with this assumption. And later on, you can probably try to check if this assumption makes sense or not. But in this case, in this discussion, it's a given. It's an assumption. When I say it's an assumption, that means it's a given. Now, whenever we put this confidence interval, our guiding principle is to look at the distribution of a sample point estimate. So we take a sample, and based on that sample, we compute a point estimate. So we are trying to find this sigma for the population, and we make a point estimate. So we know that for the standard deviation or for the variance sigma square, a nice point estimate is S square, which is just the sample variance. And why it's nice? Because at least we know that it's unbiased. The average equals to the sum to the population value of the variance. So our principle is take the sample point estimate and consider its distribution, its probability distribution. And use that to come up with a confidence interval. So if we take this to be our sample estimate, so we need to know the probability distribution of the sample variance, which we know. So these basic relations we studied in last chapter, and this is what we discussed, that the sample variance, which is a random variable, is related to a standard distribution, which is the chi-square distribution, through this formula. And this is the connection. Here is given this is the parameter you are after. Parameter we need. And we can use this relation and draw this distribution, and from there we can construct a confidence interval. Now this formula, you have to remember, this works only for normal population. This variable itself is not normal. S square is not normal. When I say it's not normal, I mean it's not normally distributed, but the population is normally distributed. So this chi-square variable, it also has this index n-1, so depends on the sample size. And for each index n, you get a different plot. But they look something like this. Start with 0, cannot take any negative values. Well, let me make it heavier over here. Okay. So this is the chi-square, but this would be also be the shape of S square, because S square and chi-square are proportional. There is just a constant proportionality factor. So this shape describes the distribution of your variable of your sample estimate S square. So this distribution is telling you where your S square can lie in a particular sample. And when you pick a particular sample, when you do an actual experiment, take a sample, you will lie somewhere, let's say here, and you want to make a confidence interval around it in some fashion. So again, the logic goes that you have somewhere here, you have the mean of this distribution, which is equal to, let's say this was S square, which is equal to the, according to this formula, to the population variance. If I consider this to be a graph of S square. And then you can draw some interval around it, like this. So that you have a certain beta probability of the S square lying within this in a particular sample. So you will use this to put beta times 100% confidence interval. So taking this size, you want to put a you get in an experiment, you get the value for sample variance somewhere here. You want to put a kind of a interval around it so that it contains your average value of S square, which will be equal to the population variance. Now there's a complication. So this is exactly the same logic which we have been choosing, but in this case, there's a slight complication. What's the complication? Well, although it's true that this is unbiased, however, this chi-square distribution, which is just proportional to S square distribution, is not symmetric. So like its probability is more concentrated, for example, on this side. So your mean is pushed like over here. And like half of the probability is here in a small interval, while half of the probability, let's use this color. Well, the other half of the probability because it's tapered over here, is contained in a longer interval. So because of this asymmetry, when you get a random value over here, you should take care of this asymmetry. And you should draw, so to speak, a bigger interval on this side and a smaller one on this side, depending on where you land, so that you have a specific probability of containing this value of the population variance inside your interval. So we don't, so that's the main idea, that there's a asymmetry, so we have to take care of that. And actually we can do it very easily if we just use the probability algebra. So what do we want? We have this variable chi-square. So we want to select this interval. We want to see what is this size. So I just give it some name. The value of chi-square A. When this chi-square variable is between these two values, chi A and chi B, then you have your desired total probability beta. So this is equal to n minus 1 s square over sigma square. So over here, I can invert these probabilities, and I can, given a particular s square, I can find what is the probability of sigma square being a certain value. So I just take it on this side. So this probability which says that this number is within this range can also be written that when I take this sigma square here and bring this here, it says that sigma square is less than, because sigma square comes here, is less than n minus 1 s square over chi square A. And it's greater than, when I bring it here, n minus 1 s square over chi square B. And you notice that B is the upper value and A is the lower, but it goes in the other way around in this formula. So this is equal to B, or which I can also write as 1 minus alpha, where what is alpha? This part above chi B, this has area alpha by 2. Similarly, this part below chi square A also has area alpha by 2. So that's how you can find these chi B and chi A using the distribution of chi square variable and finding these critical values. So that means since it's not evenly distributed, so I cannot pick one margin of error, and because I'm not making the same size of interval on the two sides of my point estimate. So I cannot just compute one margin of error and add it to my point estimate to get the upper confidence level, or subtract it from this point estimate to get the lower confidence level. I have to compute them separately because they occur at two different points. They're not halfway. The point estimate is not halfway between this interval. So I have to compute these two both. And this tells me how to do it. This is what it's saying, that to get this probability beta, this is your upper confidence level. And what is this chi square A? It is this number. So how can I find it? I can find it in many ways. For one example is This is just the cumulative probability of this chi-square variable equal to alpha by 2, this cumulative area. Similarly, this is the lower confidence level. So here I have to put B. What is B? You can either say that this is the probability of chi being more than a certain value, so that the probability is alpha by 2. Is that critical value of chi, so that the probability of chi being more than that is alpha by 2. Or if you want to write it in terms of the cumulative probability, then this is just, you have to come to this number. So you are adding all this area. So is the total probability of chi being less than 1 minus alpha by 2. So it is this number. And now the problem is simple. All you have to do to compute this confidence interval, you have to compute these two numbers, upper confidence level and lower confidence level. These would be the boundaries of your interval. And how do you do it? You have your point estimate S, you have your sample size, you just have to compute these critical values from the distribution. So let's demonstrate this with an example. So suppose you are shipping a big consignment, and let's say it's some kind of a, let's say medicine, where you have a very specific amount of a certain chemical. And you do not want it to be changing much, but obviously you cannot make sure that you always get exactly the same amount. There's always fluctuations. So this value of chemical is, you assume, is fluctuating a little bit because your process is never perfect, and it's normally distributed. There would be some variance in the amount which you don't know, and you want to make sure that that variance is small, it's equal to certain number x, it's at least less than this, which you don't know, which you have some tolerance level, so you want your variance to be less than this number. How can you make sure? You have a big consignment, you're not going to check every tablet over there. So suppose you take a sample of size, you pick 15 tablets, and you measure the values of the amount of chemical in it. You get these 15 values. You compute the standard deviation, sample standard deviation, and let's say you got this number. This is just an example. Based on this, what can you say that what is the standard deviation of this chemical in the whole population? So that's the question. So is there still a question? Someone raised the hand. Yeah, Shahrukh.
Sir, variance should be less than क्या लिखा आपने?
Some number x square.
Okay.
So you have some quality control that variance should not be too much. and you're now trying to measure the variance of your consignment. How are you varying it? How are you measuring this number for the consignment? By just taking a sample. So you say that let's put a find a 95% confidence interval that confidence interval for the variance, or let's say for the standard deviation of the population. So if you have computed this interval, then you will have a fair idea of what range could be the standard deviation of my whole consignment. So you have n is equal to 15, and your sigma, your S is 2.36. So we just pick this formula to compute the upper confidence level. So it's going to be 14, which is n minus 1, times 2.36 square, divided by this critical value. So it's a 95 interval. So the alpha would be 0.05. So this is going to be 0.025. This number comes in here. So let's do it on SPSS. So I have, let me put in some data here. I have this sample variance, which is 2.36. So let's give it a name, sample variance, and let's increase its decimals a little bit. And I want to compute this critical value. So let's go to compute variable, and I'm going to store it, this critical value upper, let's call it this. It's not really upper, it's the lower one. I'm just calling it upper because this I will use to compute my upper confidence level. So you go to, because I'm computing the critical value, so I go to inverse distribution, and the inverse is of the chi-square. So the probability is 0.025, and degrees of freedoms are 14. So I get this answer, 5.63. Well, let me just increase its decimals a little bit. So that's the answer I get for the upper critical value. And the upper confidence level would be, let's say, upper confidence level. According to my formula, it's 14 times 2.36 times 2.36 divided by this critical value which I just computed. So it's 13.85, but that's the upper confidence level for sigma square. So maybe I could have taken the square root of it. So I go to arithmetic, square root. So this is the number I get, 3.72 for the upper confidence level. It's just that I have put these numbers in the formula. Now to get the lower confidence level, I first compute that critical value. So let's say critical value for the lower, which will be used. And again, I go to inverse distribution functions, inverse chi-squares. And this time, what would be the probability? Well, if I go here, so this is for this critical value. And this, if I sum, cumulative probability is 1 minus alpha over 2. So it's going to be 0.975. And again, 14. And I can now compute the lower critical level. So not lower critical level, a lower confidence limit. Yes, Alizan, what's your question?
Sir, if we do this from the table, we take
Yeah,
the
I'm going to do it
probability
from the table as
0.9.
well. I'm going to do it next with the table. So again, I go to inverse, not inverse, I just need some arithmetic operations now. So I need to compute the square root. Square root of 14 times 2.36, which has to be squared. So I can just square it by multiplying twice, divided by this critical value, which I just computed. Critical value lower. So 1.73 and 3.72. So that means my confidence interval is between 1.73 and 3.72. While this was my sample variance, which had to lie somewhere here. It belongs here. And around it, I'm creating something. And you can see that it's, this was my 2.36. This thing is over here, while this has a longer range. It's not symmetrically distributed around your point estimate because the probability distribution itself is not symmetric. So let's do it using the table. Let me open. So let me just open the book. Just give me a second. Okay, I got the book. And let me go to the corresponding table. Wait, let me share it again. Okay, so first I want to compute the upper confidence level. I needed this thing. Chi-square 14, 0.025. So this thing, this thing over here, so that the cumulative probability is that critical value, so that the cumulative probability of chi being less than this value is equal to 0.025. So if I go to my book here, this has these index that which chi I'm going to use. But if you look at this, the way they have drawn these critical values, to pick this number over here, where, let's see if I can write. Okay, let me just point at it. I need to get this number so that this white area is 0.025. But that's not how they are drawing it. They are giving you the values for this shaded blue area. So these are the lower critical values. That's how they define it. So it would be that, let me increase the size a little bit, that chi-square is less than this critical is, so you're computing the total probability that chi-square is bigger than this critical value, and that's equal to alpha. So the total probability that chi-square is bigger than this critical value would be then 0.025, 1 minus 0.025, because this white area is 0.025, while they are giving the probabilities for this blue area, which would clearly be 1.025. So I have to look in the table where the probability is 0.975 and the number 14. So it gives me point 5.629.
Sir, we'll check at 14, right?
That's what we had over here, 5.629 in our SPSS computation, and that's exactly what we get from this table, because 14 is
So,
our
sir, the standard.
Hmm?
Sir, so sorry, I'm cutting you. Sir, the standard deviation so is basically it's greater than A, right? Chi A.
Standard deviation
shaded
is not.
region.
That's not standard deviation. That's just a critical value of this variable chi-square, which we need in our computation for the standard deviation. And as you can see, that this is how we are writing it, that you have a beta, which is, for in our case, is 0.95, which defines your confidence level. From this, you compute alpha, which is just 1 minus beta. And this critical value, to compute this critical value, you need, we had defined it this way, that chi-square is less than this critical value, let's say just C is equal to alpha by 2. But the book is not giving it like this. It's giving it, for these lower critical values, it's writing it chi-square is greater than this critical value. So if it's greater than that, that probability would obviously be the rest of the area, which would be 1 minus alpha by 2. So that would be 0.975. So that's, I look over here. This is the probability of exceeding the critical value. So that if I look at this probability 0.975, I look at the index 14, I get 5.629, which is exactly the value we had calculated over here. So I compute again, so this critical value, chi-square 14, my table tells me it's 5.629, and I use it in this formula. And the rest is just a calculation. So you can get this upper critical level. Now to get the lower critical level, I need this critical value. So that this probability is alpha by 2, which in our case is 0.025. So these upper critical values, so these were the lower critical values, as you can see here. To go get the upper critical values, you go to the next page. And here is just giving you the probability that your this chi-square variable is greater than this number. So this chi-square, this one, is in this case, it's just computing this area, which is just equal to 1 minus, which is just equal to alpha by 2. So that's directly 0.025. You can see it from this shaded region. So I look at 0.025, I look at 14, and it gives me a number 2.145. Let's see, this is what the SPSS gave us. 625. Yeah, 2.145. So 0.025 is the probability of exceeding the critical value is 0.025, number is 14. This is T distribution. This is not the chi distribution. It's over here. So 0.025. Always read the graph which you are reading. So it's upper critical values of chi-square. So 0.025, number 14, it gives you 26.119. And that's what we had over here, 26.119. So you just put it in your formula and you have the answer for lower critical level. I'm writing it this way because that's how I have been defining it. But it's very clear what you have to do in the table because this is the number. This is the number you are looking for. So let's do another example. So suppose you are given this data. Let me not make up any practical example. You just pick a sample of size 9, and this is your data. You want to estimate 90% interval, confidence interval for the population standard deviation and population is normal. So all you have to do is pick these numbers and compute their sample standard deviation. So you can either compute it by hand. So you know what you need to do. You have to first compute the mean of these numbers, then compute their differences, take the square and sum them and add by and divide by n minus 1. So you compute x bar, which is sum of all these values divided by n, and then you compute x bar minus all these values squared sum over I divided by n minus 1. So that's your s square. You can do it with a calculator. If I do it with SPSS, then I can just type in this data, 21.2, 18.6, 20.4, 21.6, 19.8, 19.9, 20.3, and 20.8. So I had these 9 data points. I can just analyze them. Go to analyze, go to descriptive statistics, go to descriptives. And all I need is the standard deviation. Well, if you want, you can keep the mean. So your mean is 20 and your standard deviation is 0.88741. So your S is 0.887. And you want to put in confidence intervals. So its beta is 0.9, alpha is 0.1, and you're looking for chi-square 8, this critical value, 0.05. So this is your chi-square n minus 1 alpha by 2. And if you look over here in this formula, this is going to give you the upper confidence level. So let's just look it up in over here. And it's saying this symbol means that this area up to this critical value is 0.05. But in this table, it's not this area. So I look over here, it's the area which is the complement of it, 1 minus this one. So my alpha by 2 is 0.05, so I'm looking for 0.95. It's the same critical value, it's just defining it as is that critical value for which the probability of chi being more than this critical value is equal to this shaded area. So for us, it was the probability of chi being less than this critical value is 0.05. Then obviously the probability of chi being more than this value is going to be 0.95. So I pick up this probability 0.95 and the index is 8, so it's 2.733. And the other, for the lower critical level, I will need this chi-square 8.95. So this guy, so I go to this table, and because this time this area is just 0.05, I look over here, number 8, it gives me 15.507. Now I put them in this formula. N minus 1 s squared divided by this. This is the upper confidence level for sigma square, n minus 1, which is 8, and s square, s square is, what was s? S is 0.887. Its square divided by this value. It gives me 8 into point. Well, it is the upper one, so I have to use this value. Eight times 0.887 times 0.887 divided by 2.73. So it's 2.305. And if I want the upper critical level for sigma, that's just going to be the square root of it. So it's 1.518. Similarly, you can find the lower critical level of sigma, Let's write it directly. And over here, you put in this number. 15.507. So 8 times 0.887 divided by and square root. So it's 0.63. So your interval is from 0.63 to 1.518. Any question about it? Now let me consider, yeah. Here. So this was the data. It was 9 points in the data. So I computed the standard deviation of the data, which is over here. And I had to put a confidence interval of 90%. So that gives me an alpha of 0.1. And that means I have to compute these two critical values, this and this such that this area is 0.05 and this such that this area is 0.05. This value goes in because it's a smaller value and you're dividing by it, so it goes in to give you the upper confidence level. And in the formula, you are just putting in the number times the sample variance divided by this critical value. So those numbers went in here, and then I computed this number, and that went in to give me the lower critical level, lower confidence level. Now you can do another kind of case. So let's say this is case. Yeah, Lizan, what's your question?
Sir, which chapter is this in our book?
This is 8. This is 7. And this is, we are just about to finish this chapter today. So I had called that case 4. Doesn't matter what you call it. Yeah, what's your question, Alizan?
Sir, one more thing, sir. When do we differentiate when to use a Z table and when to use a chi table? Like,
well, you
can
have
just
to
tell us one more time?
you have to listen to the lectures carefully, go and review them, do some homeworks, do some problems from the book. When you do chi-square, we have discussed it. When the chi-square is relevant, when the t is relevant, when the normal is relevant. So every variable you are discussing, different variables have different distributions, and you have to remember. So these are like some of the things in this course which you have to remember, that which variable has which distribution. So like we know that the variance, sample variance, that has a chi-square distribution. And we know that the sample mean has a normal distribution. And we know that if I compute a variable, I try to make a variable which is a division of the sample mean with the sample variance. So that kind of a variable will have a distribution, t distribution. So that would be relevant when you do not know what is the variance of the population and what is the mean of the population. Then what becomes relevant is the t distribution. Yes, Shahrukh?
सर इसकी लॉजिक ये हो सकती है ना कि वेरिएंस की फार्मूला में स्क्वायर आता है तो इट हैज़ नो नेगेटिव वैल्यूज, जिसकी वजह से chi स्क्वायर डिस्ट्रीब्यूशन होगा.
This is not the logic, but this is a nice way to remember it. But you
Okay.
still have to remember that chi square is the one which has no negative
Negative value.
value. So these are just various distribution. Like we are not doing a very theoretical course where we derive that why these variables have these distributions. That would be a mathematical course. We are not doing it. So over here, you just have to remember that which variable has which distribution. And then you use those distribution using your standard calculators from SPSS, from internet, or from these tables. So based on what we have discussed, we can actually invert the logic to get something else. So for example, we can do this kind of problem. So get beforehand the sample size needed to restrict the margin of error to a desired level, to a desired limit, let's say, with a specified probability. So you are going to sample. So for example, you are going to estimate the mean. We know that there's no exact statement in saying that when you sample and you get from there, you get a point estimate, but that's not going to be the actual mean of the population. And the best you can do is around that estimate, you make an interval and you say that the mean is over there. But this interval, how big or how small it is, it also depends on the sample size. If you make a small sample, then this interval is larger. For smaller samples, confidence interval is large. And for bigger samples, confidence interval is smaller. So you can control that what would be the confidence interval. What is like when you make an estimate, you expect some error around it. You can restrict this margin of error by making a bigger sample size. So beforehand, before even making a sample, you can compute like how big of a sample you would need to restrict this margin of error to a desired limit. So let us do this kind of thing for the mean of population. So let's say it would be finding the necessary sample size for the mean of the population So what's the logic? The logic is exactly that you're using your formula. Since you know that with beta times 100 percentage confidence interval is given by, this is your point estimate plus minus this. Because why this standard normal came in? Because I am estimating the population mean. For that, the distribution used is the standard normal. So this is just using the formula from previous lecture. So the margin of error was given by, so that means I can specify a margin of error and compute n. If I know the population standard deviation, n can be computed for any desired margin of error. So let's quickly do an example. So suppose you want a margin of error to be less than 5. So that means and I'm looking for the minimum sample size I will need. So for that, I can put margin of error to be 5. If I exceed than that, the margin of error is gonna only decrease. And I know that the population standard deviation is 40. And I want to be sure of this margin of error with 99% confidence level. So this margin of error would be for a 99% confidence interval. So all you need to do is, your margin of error is 5. So you have to put in, you have a 99. So beta is 0.99, alpha is 0.01, and you are computing Z alpha by 2. So Z 0.005. Squared times 40 squared, because 40 is sigma, divided by margin of error squared, which is 5 squared. Now I need this value. So let's do it using the tables. So this table is at this page. So I need a probability. So remember how I'm defining this one. This Z 0.005 was defined. This is the normal. Is that this area is 0.005. However, I can also find it by using the cumulative probabilities. So the cumulative probability would be 0.995, that the Z is less than this critical value. That probability is 0.995. And these are the cumulative probabilities which are labeled in this table. You can tell them by looking at this graph. He's shading the area below this critical value. Now, this book hasn't listed the critical values. So you have to go and look up your desired probability. So over here, I just look it up that there is a 0.9949 and 0.9951. I can choose any one of them because I need the number 0.995. So any one of them would do. There would be a slight difference, doesn't matter. And I just look it up. It's 2.5 plus 0.07. So 2.57. Or if you want to use this, then it's 0.08. So 2.57 or 2.58. So I put that here.
Sir, I've noticed some questions will take the in-between value of 2.57 and 2.58.
Yeah, that's what I said. So just take any one of them. It's just
No. As in they would take 2.575.
you don't have to be that accurate. And especially in case of n is going to be, you need an integer over here. And this number you will get will not be an integer. So you just add something, round it off to a bigger integer because you want to get a size so that the margin of error is less than that. So if you slightly overestimate, that's even better. So like, for example, if I do this number, times 40 times 40 divided by 25, I get 426.0096, but you can just round it off to any one you like, 4.26 or 4.27. Gives you some rough idea that what should be your sample size. So similar logic you can apply to population proportion. So suppose we use the same logic to population proportion estimates. We had said that margin of error for the population proportion is computed like this, because population proportion is still a normal variable. It's normally distributed. That's why the standard normal comes in its formula, where this is your point estimate of population proportion, but point estimate, so you're doing it to sample point estimate, which is just the sample proportion divided by n. Now, this p hat, this depends on your sample. When you will pick a sample, you will get a number. But you are trying to first get this n by specifying a margin of error. So what number should one put in for p hat? Well, the thing is that p, 1 minus p, has the largest value .25, because it increases when p goes from 0 to 0.5, it increases and then it decreases. So even if you put the maximum 0.5 here, then you have 1 minus 0.5, so that gives you 0.25. So this has the largest value. So that means if I bring in here, let's say I square everything, p 1 minus p over n. So n is just n is proportional to this number. And you want to overestimate it. You don't want to take any risk, because if n would be a small, margin of error will increase, and you don't want it to be increased. So you take this to be the largest possible value of p1 minus p, which we just saw is 0.25. So your formula becomes 0.25 Z alpha square margin of error square. So like, let's take an example. So you want to do a survey for the favorability views for certain politician. Favorability of politician X. And you want to get to the answer with a certain margin of error. You want to make the margin of error as small as you like, but you know that if you reduce the margin of error, the sample size will be larger. You will have to interview more people. So you have a certain margin of error in your mind. You say that I'm going to get to this answer, the favorability of a politician, with 3% of margin of error. And I can say with a probability, even if you specify a margin of error, you're only getting answer with a probability. So you say with a probability, let's say 99%. So then according to this formula, you will just always put 0.25. And we had just computed this value. We have to put in over here, beta is 0.99, alpha is 0.01. So we had computed this thing, and this had turned out to be 2.56 or 58. Was it 58? 58. So I put in 2.58 square, and margin of error is 0.03 square. So when I compute, .03 divided by 0.03, I get a number 1849. So if I, let's say, take a sample of 1850, then it doesn't matter, like if the population is large enough, it doesn't matter how much is the population of the country. That's how they do it. You just take this big of a sample and you have a 99% of chance that if your sample is random, you are not putting in any bias, then you are getting to this number with 3% margin of error. Whatever number you will get, so what will you do? You will just compute this. You will take a sample of 1850 people. They will answer, they see them favorably or no. So you just pick the number of yeses divided by 1850, multiply by 100. That gives you the percentage favorability. And you know that this answer would be whatever after you study you will find will have a plus or minus 3% of error with 99% confidence level, confidence interval. And so why I used this proportion formula here? Because it's a binary question, yes or no. Do you see them favorably or not? So in your population, in your sample, you are just making a proportion and then extrapolating from that proportion, a proportion over the population. What percentage has an answer yes for this question or no? So any question?
No, sir.
So let me stop here.